December 7, 1995. California, Mission Control at JPL. A giant board ticks down the seconds. T-minus 58 minutes. Somewhere a billion kilometers from where I'm sitting, a machine we built on purpose to die is already falling. It was never meant to come back. That was the plan from day one. I still pull up the old footage from that room sometimes. The engineers' faces, the cold coffee nobody finished, one man pacing while another just stares at his shoes, a kid in the corner with his collar half undone. I wasn't an engineer. I was the secretary who kept that floor running, answering phones, fetching coffee, typing memos nobody read twice. That day I stood by the doorway with a stack of unanswered messages in my hand and forgot to deliver a single one. They had sent something like a child off alone, straight into the most hostile sky we know of, and it had less than an hour to tell us anything at all. And there we stood, useless, unable to lift a finger to help it.
But first, you need to understand exactly where we sent it. Jupiter isn't a planet the way your school books drew it. There's no ground to land on. Not solid, not liquid, nothing you'd recognize. Drop something there and it just keeps sinking. Through gas, then through gas squeezed under crushing pressure, then through liquid hydrogen, and then through liquid hydrogen so compressed it stops behaving like a gas at all, and starts conducting electricity like a strip of copper wire. Somewhere far beneath that, in theory, sits something resembling a core, roughly Earth-sized. Or maybe it isn't a core at all, just a smeared, fuzzy zone of heavy elements bleeding gradually into the rest of the planet through layers of density no lab on this planet could ever recreate. Nobody really knows. You can't land on Jupiter, and it has nothing to do with our technology falling short. There's simply nothing solid enough to land on. The word landing doesn't apply here.
Everything we've thrown at Jupiter for the past 30 years hasn't been a landing mission at all. It's been a falling mission, a brief window to phone home before the planet crushes the messenger. 70 minutes is roughly the ceiling of what we can manage. Galileo launched back in 1989, riding the shuttle Atlantis into orbit before a long, looping 6-year detour past Venus and twice past Earth, borrowing gravity the way a hitchhiker borrows rides because the rockets of the time had no fuel for a straight shot. The main spacecraft was an orbiter, built to settle into orbit around Jupiter and keep working for years. Tucked inside it rode something smaller, an atmospheric probe weighing 339 kilograms, about the size of a small dinner table. Most of that mass was a single thing, a heat shield. That shield was an ablative composite, engineered to burn away layer by layer, sacrificing itself to soak up the heat of entry, the way a worn-out brake pad wears thin so the rest of the car doesn't stop working. Packed tightly beneath it sat 6 scientific instruments, each no bigger than a pack of cigarettes. This probe was built around exactly one job: reach Jupiter and fall into it. Not survive, not return, just send back whatever it could before the end. In July 1995, 5 months before arrival, it separated from the orbiter and kept going alone. No engines, no steering, nothing but a pure ballistic plunge. On December 7, 1995, at 22:24 Greenwich time, it punched into the upper atmosphere. And here's the part I still can't watch without holding my breath. Entry speed, nearly 48 kilometers a second. In a single second it covered the same distance a passenger jet needs 3 minutes to cross. The heat shield took on a temperature of 15,000 degrees Celsius, more than twice as hot as the surface of the sun. For 2 minutes, the probe wrapped itself in its own short-lived star, a tiny sun built solely to shield whatever was riding inside it. The deceleration force hit 228 Gs, 228 times the pull of Earth's gravity, enough to tear a person apart in a fraction of a second. By the close of that second minute, the probe had slowed from 48 kilometers per second down through supersonic and finally into subsonic speed. The heat shield was jettisoned, the parachute snapped open, and from there the descent turned almost peaceful by comparison, slow, quiet, falling rather than diving. It radioed up to the orbiter, hanging 130,000 kilometers overhead, which recorded everything and relayed it home. Here's what came through during those 58 minutes.
The upper atmosphere held far less water than any of our models had predicted. Enough of a gap to knock down half the existing theories of how Jupiter had formed. People in that control room kept running the numbers back through their calculators, refusing to believe what they were reading. The atmosphere, meanwhile, turned out denser and hotter higher up than expected. Something up there was heating the gas, and to this day we don't know exactly what. Winds were clocked near 600 kilometers an hour at cloud level, and not in gusts. That was the steady baseline. About an hour after entry, the pressure around the probe had climbed to 22 atmospheres, the temperature to 152 degrees. Then the signal thinned out. The radio link cut. The probe kept falling for a while longer in silence. Roughly 105 minutes after entry, the parachute melted away. The aluminum pieces followed soon after. By the next morning, every trace of it had vaporized into Jupiter's atmosphere.
I went back later and looked at the raw telemetry. Not video, just lines of pressure and temperature, point after point. Each point meant the machine was still alive, still talking, and then the points simply stopped. That blank space at the end of the graph is something I've never quite managed to put into words. 20 years passed before we went back. A second atmospheric probe would have been an extravagance we couldn't justify. A plunge buys you minutes, an orbit buys you years. So Juno launched in 2011 with the opposite philosophy: don't fall, circle. But circling Jupiter means repeatedly diving through its radiation belts, second in violence in our solar system only to the Sun itself. Jupiter's magnetic field is 20,000 times stronger than Earth's, and inside it electrons get whipped up to nearly the speed of light. Every pass through that high-energy zone is a blow to the electronics, and every blow leaves damage that never heals. The fix was essentially a vault.
Inside Juno sits a titanium box, roughly a meter on each side. Walls a full centimeter thick. 200 kilograms of solid metal standing guard. Inside that vault, the spacecraft's brain, its command systems, its main processors, its own dedicated power. Without that box, Juno's electronics would have cooked into scrap on its very first orbit. With it, the radiation dose drops by roughly a factor of 800. Juno's orbit is long and deliberately stretched thin, 53 days from one end to the other, designed to spend as little time as possible inside the danger zone. Dive in, gather data, swing back out, recover at a safe distance, then dive again. Its first close pass came on July 4th, 2016. Since then, it has flown 34 loops in its primary mission and another 42 in its extended one. 9 years total spent inside the most punishing radiation field anywhere in our solar system for electronics. And here's what it taught us. Jupiter isn't built the way we assumed.
There's no clean, defined core. Heavy elements like silicon and iron are smeared across an enormous portion of the planet, thinning out gradually toward the center. Scientists now call this a diluted core. Researchers have spent nearly a decade rewriting theories of how gas giants form because of this single finding. At Jupiter's poles sit cyclones the size of entire continents, 9 of them ringing the North Pole, 6 around the South, arranged in tidy geometric patterns and holding their shape for as long as we've been watching, going on 10 years now. This past February, Nature Astronomy published a paper titled something like, "Juno Refines Jupiter's Size and Shape." The old figures had rested on radio data from the Pioneer and Voyager probes back in the 1970s, numbers we'd treated as fixed for 50 years. It turns out the planet is shaped slightly differently than what's printed in our textbooks. The new model is sharper, and it's already become the baseline astronomers use to calibrate the exoplanets we keep finding around other stars. The machine is dead, and its data is still pushing science forward. September 30th, 2025, the official end date of Juno's extended mission. Pause here, though, because there's a wrinkle worth mentioning. Cassini, our spacecraft at Saturn, went out with theatrics, a deliberate plunge into the atmosphere so it would never accidentally crash into an icy moon and contaminate it with Earth microbes. Thousands watched the livestream, engineers in the control room applauded. It made headlines around the planet. Juno didn't get that kind of send-off. In October 2025, the US government shut down. NASA couldn't officially confirm whether Juno was still transmitting. The agency's following year budget was sliced almost in half, and Juno's mission was zeroed out in that trimmed budget. Unlike Cassini, Juno never dove with a farewell message.
It's simply drifting. Its orbit will naturally decay over time, the ellipse tightening toward the planet, loop by loop. Maybe a year from now, maybe several years out, it will slip into the atmosphere with no camera rolling, no audience watching, simply because gravity doesn't check in with government budgets before doing its job. It will be an echo of December 7th, 1995, minus the volume, minus the packed JPL room with its countdown clock, minus the graphs everyone leaned in to read. The machine we engineered to outlast Jupiter's radiation better than anything else we've ever built will end up outlasting our own attention to it. If you've made it this far in the video, go ahead and hit subscribe. I followed this ending closely last summer and fall, reading every update as it came in. It's a strange feeling watching a machine off to its end and realizing you might be the only one watching. Subscribing is your way of saying you were here too. So where are both machines now? The Galileo probe sits roughly 160 kilometers beneath the cloud tops. Whatever atoms didn't vaporize instantly have been smeared across a vast stretch of atmosphere by convection currents. Jupiter doesn't give back what it swallows. The thermal churn of a gas giant works on a timescale of millions of years, like a slow-motion cement mixer that never finishes its batch. Pieces of that probe may now sit at depths where the pressure reaches 1 million atmospheres and hydrogen behaves like a metal. The Galileo orbiter followed it down the same path. In 2003, NASA deliberately steered it into the atmosphere, the same logic as Cassini's ending. You don't leave a radiation-battered spacecraft drifting near a moon, Europa, that might harbor life. The orbiter hit the atmosphere on September 21st, 2003. At the same 48 kilometers per second the probe had clocked 8 years earlier, and the very same planet. Juno will be the third to join them. If the probe had somehow survived the crushing, it would have kept falling toward that maybe core, that might not be a core, for hours, maybe days. Our best estimate says it would fall until the pressure outside finally matched the strength of the toughest material we know how to forge, which means very, very deep. Possibly never, because past a certain point, hydrogen stops behaving like something with edges at all. There's no boundary there between liquid and metal, no threshold where anything could come to rest. Jupiter is a planet built entirely out of you can't. Here on Earth, we have graves and monuments. We lay our dead to rest where we can visit them. Jupiter holds 3 of our instruments, and no one will ever walk out to see them. No one will dig them back up. For thousands of years, they'll remain woven into the atmospheric chemistry of a planet we only wanted to touch for a moment. That's the real gravity well, not for the probes, for us. We keep launching our most sophisticated machines into this planet, and every single one of them stays there forever. Back to December 1995, to that room at JPL, to the people standing in front of the countdown clock.
Some of those engineers, in all likelihood, lived long enough to see Juno's quiet ending in September 2025, a machine born from the lessons of everything they'd lost 30 years earlier. That's a rare kind of luck. Most major space missions outlast the careers of the people who started them. You build the machine, you retire, the machine keeps working without you, and then, a decade later, it dies quietly on some other world. We may be the only civilization on Earth that buries its own tools on other planets, and increasingly, never brings them home. Maybe we won't be the only such civilization in the universe either. As for Jupiter, it just sits there, holding its orbit, waiting to see what we send it next.